Okay, this is a variation of video number 26 that dealt with a square composite plate, which is simply supported on all four edges, and it's subjected to an impulsive pressure load. In other words, a load that is pressure on that face. However, it's not applied slowly, it's applied instantaneously, and therefore it makes the problem a dynamic problem. The difference between the problem that I'm doing right now, and this is video 27, and the earlier one, 26, is that the pressure, although it's in the previous case, the pressure was constant, instantaneously applied. However, here, the pressure is varying as a function of time, okay? It's still a dynamic problem, but it is not constant anymore, okay? The pressure is not constant anymore. You have to specify the variation of that pressure as a function of time, and that's what time modulation is in Catia V5, okay? So let me move on to let me move on to the slideshow presentation. In case you have not done video 26, you want to know what this is all about. Uh, so we have a simply supported square plate here as shown, okay? And the simple support are represented by these boundary conditions. In other words, no displacement in the vertical direction, and depending on which you either fix U or V, okay? The pressure here, as you can see, is varying with time. At least that's what it says. I'll show you how the variation looks like. Now, I'm using a very simple composite plane, only two layers. Okay, this is called a cross-ply laminate. Cross-ply laminate, 0 and 90 degrees, two of them only, and it's these are symmetrically placed about that reference surface. Okay, uh, saying that this is symmetrically placed about that reference surface does not mean this is a symmetric stacking sequence. You can see it; it's not symmetric. Okay, now here is the way we're going to define our pressure load as a function of time uh, in terms of this graph. So the first for the pressure is applied, of course, this 100,000 psi that is up, or Pascal, not psi, Pascal. This is applied immediately, and therefore the problem becomes dynamic. But as time goes on, that pressure that's applied on the face is varying with time. So uh, after 0.1 millisecond, okay, the pressure begins to drop, and within 1 millisecond, it drops to zero, and then it's going to stay zero up until time 0.4 millisecond. So this is the total simulation time that we're going to do. And please note that the fact that the pressure drops to zero does not mean this problem is going to is going to uh, uh, is going to static loading, because the plate is vibrating because of that initial applied pressure. Okay, it's vibrating, and once you drop the pressure to zero, that vibration is not going to go away. It's going to stay there unless there is damping, of course. Now, curve like this, if it was maintained as 100,000 Pascal, just like video 26, then although I can define a curve like this, which is a constant 100,000 uh, Pascal throughout the simulation time, a constant, but CATIA has made it easier for us. You can call it a white noise. So the modulation is basically a white noise, which is going to be 100,000. You don't have to give it a curve. But if you have a variation like this, then you have to give this information to it, and it's going to be done through an Excel spreadsheet, or you can do it through a text file too. But I'm going to use Excel spreadsheet. Okay, this was white. See that this was white noise constant. But if you have variation with time, then you have to input it in the form of a curve. Now, this is some documentation from the CATIA's limited native FEA solver. Okay, you can look at it. I'm just going to move along. Now, the material properties that I'm taking are taken out of Reddy's book for a problem that they did. In fact, problem number 26 was from Reddy's book, okay? And these are the material properties that he's using. Now, these dimensions, 25 centimeter, 25 centimeter, uh, with respect to the height or the thickness of the laminate, I would have liked the thickness of laminate to be smaller than what I've got here, but I'm just using the same numbers there for, although I don't like it, but this is 5 centimeters or 0.05 meter. Now, this problem has a plane of two planes of symmetry, so in principle we can model only a quarter of that, but I don't advise doing it because uh, the planes of symmetry in composites are sometimes difficult to identify. In this case, it's easy because the angles are 0 and 90 cross play, so we don't have much problem seeing it. But in general, I don't advise it. Now, you need the density here because this is a dynamic problem. This is density, and I'm gonna use a very coarse mesh, and this is not a a good mesh for in general. The only reason I did it like this is that in the in Reddy's book, there's some comparison with the theoretical solution and finite element solution, and they use a coarse mesh just like I'm doing here. And then eventually we're going to plot the variation of this node 17 as a function of time, okay? So ultimately we want to get the variation of, for example, displacement of node 17 as a function of time, etc. Now, the process is generate the geometry, generate the plies, do a static solution first. Uh, in doing static solution, you have to specify restraints and loads, obviously. Then extract frequencies. Now we don't need the loads to extract the frequencies, but we need a restraint. So we need these. We use these restraints to do that. Okay, and then insert a transient dynamic calculation. Your phase, and in order when you do that, it needs the frequencies that were just calculated up there, and it needs the load, and then we have to give it the modulation curve. Okay, so remember that the transient dynamics solution in Catia V5's FEA solver is based on modal superposition. Therefore, you cannot do nonlinear problems, and so keep that in mind. All right, I'm going to put this stuff in front of me. Let's go ahead and, okay, so the first thing we're going to do is to create a material. So start, infrastructure, material library, double click on it. I'm going to give this thing the proper name, so we'll call it time modulation. Time modulation, okay, apply. Notice that the name changes here. Composite, unidirectional, this unidirectional, and the thickness of the composite is each ply is 2.5 centimeter. Okay, this is the only thing that is used here, and none of these are relevant to the FEA calculations. And then you're going to go to analysis. It's a 2D orthotropic problem that we're doing, and these things are coming from the screen that I showed you. These numbers, okay. So the first one is 5.25 e to the 11. Next one is 2.1, 2.1 e to the 10. This is transverse Young's modulus. Okay. Poisson ratio is 0.25. G12 is 1.05 e to the 10. And this is the same thing. 1.05 e to the 10. And this one is different. It's 4.2 e to the 9. And the density is 800 kilogram per meter cube. Apply. Okay. I always habit of checking this again. So this is the thickness, laminate thickness, unidirectional analysis. Everything is what I typed in, and we say OK. And now we're going to save it. Save it in that folder by modulation. I'm going to call this thing so that we can easily identify them. Time modulation. Okay, very good. And we're going to close this. We don't need it. Now we're going to start a part file. I'm going to call it time modulation. Okay. On this XY plane, I will sketch a rectangle which is 25 centimeter by 25 centimeter, or square which is 25 by 25. Dimension it. This is 25 centimeter. And this one is 25. Okay, exit. And fill it, F-I-L-L. And join it. And as I have repeatedly said, the reason I join is that I want to make sure that I have a control over the direction of the normal to the shell element. So if I flip this, direction of the surface is downward, the direction of the normal to shell element is going to be up. Okay, let's create a coordinate system here, axis system, which is going to be used as rosette. I clicked on the axis system right there, okay, and move it off the plane because it automatically puts it at 0, 0, 0. We're going to move it to a different point. Right click, create a point, minus 10 for y. So it's going to move it to 10 centimeter over here. And make sure this you uncheck this, uncheck the current, because I don't want to use this thing as my coordinate system for what I do. The only thing I'm going to use this thing for is my rosette direction. Okay, that takes care of this. Now we're going to go to composite design. Okay, and before I do this, I'm going to save this file, save management. There is my part, save as. Is that the right folder? Yep. Say OK. Okay, now in composite design, we're going to create the parameters, composite parameters. You click on it, add the material. Remember, I created the database, so I go and retrieve it. So desktop, it was called time modulation, right there. Say OK, and we say OK. We select our rosette, add a rosette. This is the rosette. Say OK. If it's bothering you, you can always hide it. Now, as far as laminate directions go, I don't need to create anything special. 0 and 90 are already default directions, so I say OK. Good. Now we're going to create our plies, because all this was the parameters. So create a plies group. Surface is this. Direction of draping is up. I always habit of doing this, upward direction. And then create a ply, manual ply, so ply. In that ply group, for the boundary, we select the sketch right here on the outside. And for attribute 0 degrees, material was already picked. Let's do another one. Here's my ply number 1 that's created. You can see that. And this hand means that this is a manual ply. And although I created it manually, I didn't use any other automatic features such as zones, etc. So another one on that plies group. For the boundary, that same sketch on the outside. And for the attributes, 90 degrees. Okay, we can always double check that. So we go to the ply exploder, select the plies group, apply. Now notice that what happened is that they are here, but this scale was so big that you can't even see it unless you zoom. I mean, look, I can do that. I can say zoom, and it's right there, but this is terrible. So let me make this thing maybe five times, apply, and there we are. Okay, so sometimes you try to look at this, you don't see it on the screen. That's because this was too big, probably it's off the screen. Cancel. All right, good. So we're done here. You save it. Let's do that. Save. Now we're going to go to advanced meshing tool, because if I don't want a nice rectangular grid, I don't have to go there. I can go to generative structure analysis. By default, it's going to do a triangular mesh for me. I don't want that. I want a rectangular one. So I go advanced meshing tools. This is a static problem that we are doing first. You click on it. And then right here, surface measure on that surface, 12.5 centimeter. That means two this way, two that way. Remember, this was 25 and that was 25. And you mesh it. There we are. You can see that. Exit, and that takes care of this. Why don't we save our analysis? There's the analysis. Save as the correct folder. It is the correct folder. So you say time modulation. Time modulation. And we say OK. Good. Now we're done here. To apply the load and restraint and things like that, you have to go to advanced to generative structure analysis. You can see your mesh if you want. Right-click mesh visualization. It's right there. You can see that. Okay. And yeah. So deactivate this. Activate it. Okay. All right. I don't want this rosette. I'm going to hide it. Now, let's apply our restraints. The restraints, these are simply supported on the four edges. So you click on this, let's check that. So this edge, now notice that I cannot select the edges. I try to select the edge, but it picks the whole thing. That's because there are two things that are blocking my pick. One is the sketch. One is the sketch here. See that? Hide this. And also the ply boundary. So hide the stacking sequence, stacking engineering. Now I can select these edges. See that? Okay, so I select this edge and that edge. And simply supported means they do not move in the direction Y. And of course, they do not move in the direction Z. Do the other two, this edge and that edge. They do not move in the direction X and do not move in the direction Z. Okay? We're doing a static analysis first. So you click on the pressure. And on that, I put 100,000 Pascal. If I run it, it's going to complain that material is missing. Just to convince you, I'm going to do that. Look, run. See, material is missing basically. So because I did not import my composite properties, I created it in Composite Design, but you have to import it. So you click on it, import. The surface is right there, and it's done by ply. So click on the wrench, go select the ply from your tree right there. See that? As soon as I selected this, put it over there, and then symmetrically place. Symmetrically place means that it is like this, about the reference surface. Okay, and we say okay. If I did everything right and run this thing, it's going to give you a deflection of this under static load of 100,000 Pascal. And it will. It will run. You can look at the deflection. Now, you might say, oh, wait a minute. Oh, this doesn't look right. That's because the fact that, see, I've used too few elements, and this is the scale was so big that you can't see them properly. So let me double click on that. First of all, change it to average ISO. And this is a huge scale. I don't want it like that. Now, let me let me make this thing, I don't know, 100. Sorry, 100. And there we are. If that's not satisfying, make it bigger. Maybe, I don't know, make it 200. How about 500? 1,000. How about 1,000? 2,000? Still can't see much. So let's try it again. maybe 21,000. How about the 21,000? It's too much. There, you can see that. All right. So this is for visualization, visualization effect. Yeah. Now, this was a static problem. Okay. Now we have to extract the frequencies. Okay. So we go to insert. Okay. Frequency case. And it says, okay, the restraint, do you want new restraints or the old ones are good enough? Well, of course, the old ones are good enough, right? So I don't want a new one. And it says, go pick it. Okay, so I go to my static case that I did and pick the restraint. So use the same restraints for frequency calculation. That's it. You just run it. It's going to extract the frequencies. It's going to, because I said all, it'll do the static one again and it'll extract the frequencies. Okay. Now, how do we see this? How do we see the frequencies? Well, you say, yeah, okay, show me the deflected shape right there. Once again, this was the scale was too big. Let me make this thing. Let me make this thing. Uh, where is that? Let me change the scale here. Average ISO. That's a huge scale. Okay, there we are. Okay. But anyway, double click on the translation, this translation, select the occurrences, it extracted 10 frequency for you by default. You can change this to take more or less simply by double clicking on this before running it, and I'm sorry, right here, before running it, and ask for more, okay, if you want. But that's fine for me. 10 is fine for me because this is demonstration now. Now, once you get the frequencies, then you're going to go and do insert transient dynamic response. Now it says, okay, which frequencies do you want to use? Well, the frequency is the one that I extracted right there, the 10 that I extracted. I put it there. The load is going to be new, okay? So for the load, notice that the load, see the load option and restraints option, these are all dimmed here. That's because it's assuming that you already got the frequencies, therefore you don't need these restraints anymore. And the loads are dimmed here because we're going to be using the one that we applied in the static case. So let's see now. Uh, Double click on the load, see that double click on the excitation, load excitation right there. It says, okay, go select your load. The load was that pressure right there. Okay. And then it says, what about your modulation? Now, if this was a constant pressure applied there instantaneously, then I would need either a white noise or a constant curve, basically. Okay. But this problem that become like 26, video 26. But this problem, I cannot use a white noise because this is not constant. So what I need to do is have to create a curve and bring it in. And the curve is going to be like this, okay? Like that. All right, so here's what we're going to do. We're going to say, okay, we can't proceed anymore, and unfortunately, you have to get out of here. You go there, this is a white noise. Our case is not white noise. And this is with modulation. One of them is frequency, it's going to be the next video. And the other one is the time modulation. Now, I haven't created it. You see that if I try to say do this, it's going to say, okay, well, where is it? Where is that Excel spreadsheet? If I say I haven't created it, so I'm going to cancel that. I'm going to minimize this. I'm going to go to my folder right there and create an Excel spreadsheet and put it there. Okay, my Excel spreadsheet should basically reflect this data that you see here. So the first row or the first column, I'll put X in seconds, The second column is going to be the amplitude of this modulation that I'm going to define. So it's going to be Y without any units, okay? because it doesn't have any units here, because later on I'm going to take this value and multiply it by the pressure, okay, which was in Pascal. So right now it goes like this. So when x is 0 seconds, the amplitude is 1, okay? When x is 0.001 seconds, 0.001 seconds, which means 1 millisecond, the amplitude is still 1. Okay, so we're trying to recreate this curve, this height being 1. Later on, we're going to multiply it by 100,000, but the amplitude is 1, 1 at 0.1 millisecond, which is 0.3 zeros and a 1. So this is not correct. Should be 3 zeros and a 1. 0.1 millisecond is this, 0.0001. And then at 0.0002, which means 0.2 milliseconds, the amplitude drops to 0. See this? The amplitude drops to 0, and then it's going to stay 0 until 0.4 milliseconds. So this is going to be 0.0004. That's going to stay at 0. Okay. So this is going to be my modulation curve, time modulation curve. I'm going to put it in. I'm going to put it in that folder. Save as desktop. Desktop. I made a folder which was called time modulation, and I'm going to call it my time modulation. And you say save. Okay. So I'm going to close this. Notice that in that folder that I'm putting my stuff in. Okay, where was that thing? Time modulation. Of course, I have my material, my part, and my analysis that I've done so far, and the Excel file right there. Okay, so let's go back to Catia, and I'm going to import right now. See that under modulation? This is white noise. This is time modulation. Click on it, browse. You go to that folder. This is the name that I gave it, and you retrieve it. Assuming there are no mistakes, so we say OK, and it was right here. As a matter of fact, if you double click on this, double click on that, you can also say edit. It shows you the values that come from the Excel spreadsheet right there. You cannot change it from here. If you want to change it, you've got to go to Excel and basically change it from there. So we say fine. It's a good idea to give these things meaningful name, because you might have different modulations that you want to try. Okay, so now we go to load, double click. It says for the load, we're going to select the thing that we applied in the static situation, which was 100,000 Pascal. Okay, and for the modulation, I'm going to select the one that I created, and the scale factor is 1. That means I'm not going to multiply that modulation curve by anything. I'm just going to multiply it by 1. Nothing is going to change. And then, of course, it's going to get multiplied by the 100,000 pascals. So, yeah, so we say, OK. Incidentally, you can also see the graph of this under time modulation right there. You can say, I believe here, yeah, you can put the cursor on it, right click, and show me the modulation curve. This is what I had. See, 0. It's going to be height 1 up to 0.1 millisecond, and then it's going to drop to 0 at 0.2 millisecond, and it's going to stay there. Well, anyway, I just wanted to show you that it can be shown. Now, that's pretty much it. This is loading. Now, I'm going to come to this issue of damping later on. Right now, let's go ahead and run it. First of all, save it. So all I did was to define a modulation, and then double click on this load excitation, okay? And let me show you what I did. I selected the load from the static case, 100,000 Pascal, and the modulation that I defined, that curve that I defined, okay? Now, one other thing I want to do, the total time of integration, or not integration, basically the dynamics simulation. Double click on it. So we're going to go not to 10 seconds. The default is 10 seconds. We're going to go to you see now, 0.004 millisecond, right? So let me see now for a second. Uh, point, sorry, 0.4 milliseconds is 400 microseconds. Yeah, so it's going to be yeah, 0.30 right there. So I'm gonna go to, where is it? So 0.0004 seconds, okay, and 4 seconds. And how many steps? Let's make this thing, I don't know, 1,000 steps. Okay, so it's going to calculate increments of 1,000 increments between 0 and that. So we say, all right, save it and run it. Where's the run? Okay, calculate or compute. So it's going to do all three of them. It doesn't take very long because the biggest cost is in the frequency calculation. But that's already done. That's already done for you, okay? And this is just using a convolution integral or modal superposition or a Duhamel integral, which is extremely efficient, so it doesn't take very long. Now let's plot. So we go here. Well, first of all, we can plot the deflection. Don't let this thing bother you. You double click on that, you double click on this translation, and notice that you can select occurrence. And these are different time. The one that shows you all zeros is at the initial time. If, for example, I go to this many seconds, this is what you're going to get. Now we can change this thing to average ISO so that it looks like that. Okay, try it again. Double click. Occurrence. If you go to, for example, almost 4 milliseconds, it's going to go like that. If you go all the way to the end, this is what you're going to get. Now remember, you can change the scale here so that, look, this is a scale of 1. So there we are. So this is too much. So let's make it 4. All right. And you can do all kinds of things, animate, and the usual stuff that you do in CATIA, but that's not the issue here. So these things can be done. Now I want to find the displacement of that node 17. Node 17 was this node in the middle, okay, as a function of time. So the first thing I'm going to do, I'm going to put the cursor on this line. And remember, we started doing things like this in video 26 prior to that. And then you say, okay, generate 2D display and say finish. It says, okay, which node do you want to take and what component do you want to plot? Now here you can plot the displacement, velocity, and acceleration, okay? Now, see, this is displacement, velocity, acceleration, but I want displacement only, and we say fine. Okay, so I'm going to minimize this. It allows you to go and pick from the screen the node that you want to basically find this curve. So it's the middle one, this one, node 17, add, and this is generated. I can close that, or I can leave it open, it doesn't matter. And there's the curve that I'm looking for. It's this one or it's down here actually, okay? So you can say restore, or there. Now this one is actually in units of meters, so I can change it to, first of all, let me change instead of the amplitude to the actual displacement position. So right click, put the cursor on this, right click, and don't give me the amplitude, give me the real displacement. It goes like this, okay? All right, and remember, we applied 100,000 PSI, not PSI, Pascal downward, so it's going to go down, okay? And then after a while, the pressure is gradually removed, and it's going to go back to vibrating, but at the lower, basically lower amplitude. Now, what I want to show you here is the following. Let me go ahead and actually do this thing at a longer interval. For example, I'm going to double click on this transient dynamics, instead of going to 0.4 millisecond, let me go to maybe 40 milliseconds. How about that? So it's going to go to point dash 4 second, 0 point. Okay, let's try it again. 0 point. This is 400 seconds. Not 400 second. This is 0.4 seconds. 0.4 second, which is times 1,000, 400 milliseconds. So let me go to yeah, let's go to 0.4 second. The only problem is that my load was not defined up to that value. Okay, my load was the amplitude, that amplitude was defined up to 0.4 milliseconds. So let's see what happens here. 0.4 milliseconds. So I'm going to go past what the modulation was defined. Let's see if it works. Okay, so all right, let me double click on this now. See how far it takes me. Yeah. Okay, so I went too far. So let me, yeah, it probably uses 0 after that value of 0.4 seconds, 0.4 milliseconds that I defined the amplitude at. Now, what I want to do is I went too far. So I want to go here. And instead of going to 0.4 second, I'm going to go to 0.004 seconds. Okay, so that's 4 milliseconds. And show me the graph. Double click on this. Okay. So you see, remember there was a load of 100,000 and it was gradually dropped to 0. But it looks like you're getting some kind of a damping here. And the answer is yes, you are getting a damping because there is a default value for the damping that's defined in there. So you double click on this damping and notice that here it's a modal damping. Okay, and if you click on the wrench, it tells you that all the modes are damped by 1%. Okay, if you don't want any damping, so make sure that this is 0, global damping ratio is 0, no damping whatsoever, and say okay. And let's see, we have to run it or whether this is going to do the job. Yeah, so you don't have to run it. The reason you don't have to run it is that this is modal superposition. The only thing that you really needed were those natural frequencies which were extracted, and changes like that do not change the natural frequencies. It just changes the stuff that you do in Duhamel integral or convolution integral or modal superposition. But the point is that look what happened. There is no damping. So the default, it takes a default damping of 1% for all the modes, okay? If you don't want any damping, and I didn't want any damping here because I didn't say anything about it, then I had to go here to damping, and I had to change this is the type of damping that I'm using. There are other types of damping, and I changed the global value to 0. If you make this thing bigger, so for example, let's make it, I don't know, 10%, that's a huge damping, okay? So we say, okay, and let's look at the graph now. It's going to get damped very quickly, right there, you can see that. Now, the one thing I have to tell you is that the video is 26, where I did the impulsive loading, constant impulsive loading, where I didn't use Excel spreadsheet, I used the white noise, okay, as my modulation. There was damping there, but because I only showed you 2 humps, basically, you couldn't feel it. But if I had integrated that over a longer period of time, you would have noticed that actually dies out, okay? One last thing that I want to show you here is the following. Let me close this, let me close that. You don't need these. Now, uh, right. Okay, so if you want to see the the values of the deflection of this composite plane at different instances, you go and you go and select your instance, for example, that many second, and of course, the numbers will change. So let's see now. Let's go further down. This was so close to the initial one, that number. Now I'm going to choose, for example, 843, and watch these numbers. They're going to change there. And of course, that makes sense because, you know, way here, when I use the first one and the second one, the numbers don't change that much because these numbers may be so close to each other that it doesn't make that much of a difference in translation. If you want to see the stresses, you have to go ask for it. And let me see now. You put the cursor on transient dynamics right there. See that, transient dynamics? Right click, generate image, and filter it with the stress. I've done so many of these before that I'm going through it very quickly. These are the previous videos that you need to watch if you need more help. So for example, full tensor component, you say okay. This one, if you double click on it and select your currents, say more, it tells you that it's showing you the sigma x in the local coordinate system. Now, if you don't want local coordinate system, choose global one. So if you want to plot sigma x, the real sigma x, and you don't know what the local coordinate system are, so we say global, okay? And for lamina 1, and if I go to lamina 2, of course, these numbers will change. If I go to lamina 2, these numbers will change, okay? And notice that one of them is in tension, the other one is in compression, and that's because one of them is on top, 90 degrees, you put the load down, depending on at what instance you're looking at this, the top may be in tension or maybe in compression, okay? So for example, if I go and select a different time, this negative may change to positive. Let's see. Yeah, see that? Change to positive. If you go further up, it could go to negative, okay? Yeah, so by the way, this has to do with the scale, amplification magnitude, so you can adjust these. The reason it looks so ugly is that we have only few elements, 4 elements. Okay, so the next video segment is going to be doing the same kind of thing with a, a load that's varying, not as a arbitrary load. These two that I looked at were kind of arbitrary, okay? It's a sinusoidal load, which is called harmonic, transient harmonic, or sometimes it's also called frequency response analysis. All right, first I do it with a constant amplitude and then come back and use the modulation with the modulation curve to basically do the kind of thing that we did right now, but with frequencies. All right, folks.